Okay, so this is my lab 3 for circuits. Um, so table contents wise, I'll be going through the introduction, the key ideas and fundamentals, the purpose, the results preview. In terms of experiments, I'll go through the assumptions, part 1, 2, 3, and 4 of my experiment, the possible errors, and then finally the what if questions. So in terms of key physics fundamentals, I'll be going through the node rule, which is that the current going into a node must be equal to a current going out of it. The loop rule, the sum of potential differences in a node has to be 0. And finally, Ohm's law, which is electric current equals voltage divided by resistance. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel using multimeters to measure the actual values of conventional current and potential differences in the circuits, and then examine the behavior of ohmic resistors and capacitors. So results preview, the expected time constant was 6 seconds, but the actual value was 5.9679 seconds. And I'll be going a little more into depth behind the discrepancy behind the two values. And then finally, the system was the circuit, and the surrounding was everything that isn't the circuit. Experiment assumptions wise, there is no resistance in the wires or the ammeters. So for experiment 1, I had two 1.5 volt batteries, 47 and 100 ohmic resistors, two ammeters. So I solved for the current myself. So it equals the current equals in taking into account the node rule, current equals voltage times resistance. So I added the two voltages together, so 1.5 plus 1.5, then the two resistors, which would be 47 plus 100 ohms. Taking that all into account, we got a predicted value of 0.02 amps, and then on the left you can see where I actually made the diagram and then changed the ohms on the resistors, and then after doing that I got 0.02 amps, which is the same thing. The next on the bottom, I took out one of the ammeters and put in one of the voltmeters, and I found that the voltmeter's voltage is 3 volts because the current is not flowing through the wires or resistors, and then there's 0 volts from the open wires. And on the top right, finally, you can see the voltage for the round trip where I attached the two prongs of the voltmeter onto two different ends of the battery. I got the voltage equaling to 0. So next, I measure the difference in potential in circuits. So here you can kind of see node 1 to node 2. You can see the different volt changes between that. And then on the bottom between that, you can also see that graph where I graphed the voltage between the different nodes. And then finally finding the ohms for each one. I found that for the 40 resistor with 47 ohms, it was 47.45. With the 100, it was 120 approximately. And then for the wire and ammeter, it was 0 ohms. So experiment part 3 is where I had a 9-volt battery. I had 10 and 20 resistors, and then 0.2 capacitors, and then created an RC circuit containing a light bulb, battery, and capacitor, and calculate the time it takes the capacitor with both bulbs with its charge and discharge. And I found that for 10 ohms, it was 7.4 seconds for charge and 8.6 seconds for discharge. For 20 ohms, it was 7.3 seconds for the charge and 7.6 seconds for the discharge. Um, and then the final part of the experiment was I had an RC circuit with 30 ohms light bulb, 9-volt battery, and 0.2F capacitor. And the time constant for this should have been 30 ohms times 0.2, which is 6 seconds, which you see in the bottom predicted. So I took the change itself and I did the natural log of the voltage divided by initial voltage, and then the voltage is the second column where you can see it starts at 8.56, and then taking that change, I just went from 0 to negative 3.32. And then I also graphed that. You can see it has a downward slope. And so the time constant is defined by 1 divided by slope equals negative 1 divided by negative 0.173 equals 5.7659. So this is a little different, which I'll be going to. Why is because possibly incorrect timing due to human error, incorrect creation of the circuit itself, and then ammeter lack of accuracy. What if questions? What if you're doing the experiment in real life? So with the simulated ammeter, we're assuming it has no resistance. A real ammeter would have some level of resistance. The resistance of the ammeter would have created a voltage drop and affected the components of the circuit in return. If you were doing this experiment in real life and use a battery to charge a real capacitor with no resistance circuit, the ideal model would charge instantly because since it has zero resistance, it has zero recharge time. And then no, because in real life, the wires would have resistance, unlike the lab simulation. Thank you.